of the continuous numeric variables. And how do we do that? We'll use the Matplotlib, so plt.histogram. So hist method from the Matplotlib is going to be used in order to create this histogram. Histogram is just a visualized form to see the distribution of continuous data, and we'll have 10 beans. You can have as many number as you want. So we'll do it for a mileage. Okay, and there are two parameters. First one is the variable for which we want to create histograms, and the second is the number of beans. Okay, you can replace that with simply with 10, right? Instead of providing as a variable, we can simply hardcode the scalar value as well. So we'll run this, and here is the histogram. It has got 10 bins, and this is the distribution of mileage. Okay, there can be several distribution, right? Distribution in the form of histogram is just a data distribution, and we are simply summarizing data with each bean. Okay, in summary statistic we simply have just one bean, right, which is centered around the mean, or centered around the median, or the the maximum or the minimum. But here we have 10 beans, so you have distribution at different section of the data, and that's much better to understand rather than the basic summary statistics. You can see that to the right you have, if you look at the cursor, there's some observation even at 50 and 60. Okay, and that's they are typically the extreme value. So we have fat tail, right? So fat tail is just a case when you have some observations very away from the other observations. So you can see my cursor, these small set of observations, maybe a few only, but they are totally different from the other set of observations. So they are extreme to the right. In statistics we call them a typical case of a fat tail distribution, and we can remove them if we if we're going ahead with any statistical analysis. We can overlay the probability density function also with respect to the histogram. So probability density function will ensure that we get it in percentage terms rather than the actual values. Here we have the actual values, right? The actual summarized value of mileage in each bean, right? For the first, and let's say we have 25, second we have 175, something like that. But here for PDFs or the probability density function, we would be having the percentage terms, right? And the area under that PDF is always going to be 1. So that's the constraint of a probability density function curve. And here is the PDF curve. You can see all of them are in percentage terms, right? It has to lie between 0 and 1, and it does lie between 0 and 1. If you take the area under this particular curve, you will get it as 1. As I was saying about the fat tail distribution, you can see the tail is quite longer in the right hand side of this curve, right? And we need to simply remove these extreme values, and then it will look somewhat normal, somewhat bell-shaped type. Okay, and that's what is an ideal data for data analysis. We'll do that for other continuous variables like length. For instance, yes, the distribution of length looks much better than mileage. There are hardly extreme values. There are hardly the distribution is hardly long-tailed. We can also have the probability density function for this. All right. Now we will see how we can do cross-tabulation for the categorical values. Like for categorical values, we cannot obviously do the summary statistics, or we cannot do histograms or a probability density function and so on. Right? That won't make sense. But we can do the analysis just by taking the count in each category for a categorical variable. So that's basically known as the cross-tabulation, right? Cross-tabulation is of course with two variables, but not going by the definition of cross-tabulation. We simply, sort of take the count. Okay, I'm calling it as cross-tabulation, but don't take it by definition, right? By definition, it's somewhat, slightly different. So we'll use the group by method, and group by we will it will count the number of observations with respect to the different categories for a given categorical variable. Make is a categorical variable, and we will compute, or we will calculate the number of observations for each categories. Okay, how do you do that? Group by and then dot size. Okay, we run this and then we will see what's there. So here we go. We have make, and for each make we have the count or the number of observation that falls in a given category, and that's what we have in front of us. Okay, we can also plot the distribution. We can plot the distributions to various ways. We will use something called Boxplot, and obviously bar chart is something that also can be used for showing the distribution of categorical variables. We will use some of them. Okay, so so let's plot. Okay, so we can use the plot. Okay, the method in order to plot the variables. Okay, so make distribution. So make underscore dist is coming from the previous code. Okay, so we have already defined it, right? So we have defined it does have the count, and we're simply plotting the count. Okay, so count obviously is a numerical value, so this numerical value is simply plotted here. Okay, and the title, you can just give any title and just give and make distribution. Okay, you can give any title here, and here you see the distribution of the count with respect to, and visualization helps us in order to see whether a particular type of a given categorical variable is dominating that particular variable, right? It helps in sampling. Actually, in sampling we ensure that the observations are well represented, or sorry, the categories are well represented in the data. There should not be too many observations for a given category or too less observations for a given category. Then that's not a good thing for statistical modeling, something that we avoid. And then we'll do it certain things for all numerical variables and for all category variables. So we can do that. We'll first select all numerical variables. How do we do that? We use the select d type method, and we will select the data types, float and the integers. So these two data types are basically the data types of numerical variables. So it will simply select these data types. So in essence, we'll have the numerical variables in this particular list. Okay, and we call it car underscore num. That means numerical variables in the cars data set. That's exactly what we mean. And then we'll print, obviously. So what are these variables? So we have engine size, horsepower, mileage, weight, wheelbase, and length. So these 6 variables are the numerical variables in our data set. Okay, and we have combined them, and we have put it in a different data frame, and then we will do some sort of analysis on these numerical variables, something that we cannot do on categorical, like histogram. We cannot do histograms for categorical variables, right? So so this section is where I'm going to show you where you can do analysis for more than one variable. Instead of doing histogram for just one variable, how do you do it for a number of variables, all numerical variables? So here we do. we have all numerical variables in this particular data frame, and then we'll call this hist method, and we'll define the beans. Here we define the beans as 20, and we'll see the histograms for all of these 6 numerical variable just by running one line of code. It's going to take some time, but we'll have, yes. So here is the plot, and it has the 6 histogram plots for different variables: engine size, horsepower, length, mileage, weight, and wheel well. So in just one go we are able to create this beautiful plot. The next thing we'll see is the correlation. Correlation is actually a relationship between variables, and we compute that for numerical variables, not for categorical variables. So that's something we only can do for numerical variables. Now there are two ways we can do. We simply take 2 variables at a time and then take correlation of them and then keep on doing that, or we simply take the subset of the all numerical variables and compute the correlation matrix. We'll do the second thing. That's easier, right? We do it in just one go. How do you do that? We will take the car underscore data frame that we had created, the subset of variables which are numerical variables from cars dataset, and then we'll use the core method, which is going to compute the correlation for us. And the variable with which we'll compute the correlation is mileage. Okay, let's assume for a moment this is our target variable, and we want to know the correlation of the other variables with this target variable. We expect them to be very high in order for these variables to be useful. If the correlation is very less, then probably the variables are not going to be useful, right? So that's basically is what we want to see. We will run this code and then we will see the correlation, and here we have the correlation. We have strong correlation for most of the cases. As expected, the correlation between mileage with mileage is 1, right? Correlation with the same variable is always 1. Correlation also gives an indication about the direction in which the relationship are, although it is not quite correct to conclude, but it gives some preliminary indication that there is either there is a negative relationship or there is positive relationship, and wherever you have negative sign, you have negative relationship. That means one increases, the other one will decrease, and when we have positive sign, both increase simultaneously. Well, we can also see the correlation in visual forms. So we can plot the correlations, and we'll use the pair plot from the Seabon package that we had imported initially. We'll use pair plot from there, and we will plot the correlation for all of these numerical variables with respect to mileage, because that's the variable of interest or the target variable. Okay, we'll write a loop. Okay, and the loop ranges from 0 to the number of columns in the new data frame that we have created, cars underscore num, which only has the numerical variables from our cars dataset, and then we plot it, right? So for cars underscore name, this is x, so each of these variables will be in the x, and we also define what is going to be a y, which is a fixed, right, mileage. Okay, sorry, so this is the data set, this is the data frame we are providing, and here we have the index x, y and x indexes, like what we want to keep in x and what we want to keep in y. And obviously x will iterate through this loop. Well, it is going to change, and y is constant because we want to see it for with respect to mileage for each one of these other variables. So we have run it, and here are the correlation plots. As you can see, most of them have negative relationship. That's exactly what we had seen in the previous run. See, there's a negative relationship, and here also we see negative relationship. If it is downward sloping, then negative relationship. If it is upward sloping, there is positive relationship. plot between mileage with itself is something we should not even interpret, because that makes no sense. It's just have a one-on-one relationship. So we won't interpret this one, but the other ones are very useful. And you see whether there's a strong relationship, there's a weak relationship. Like a mileage with length has got slightly weak relationship or weaker relationship, because the variance is higher here. But if you see here, like weight, it seems to be a much stronger. Although we cannot conclude like that, but at least it gives us somewhat an indication. Yeah, and also these plots are useful to locate extreme values. Like, as you can see, some of the values are extremes, and we also had seen these extreme values in other analysis, and then this simply confirms our observations from other analysis, so that we can remove maybe 1% of the extreme values, or 1% of the observations which can be considered as extreme values from the data before doing any statistical modeling. Yeah. Now we have, for instance, let's say we have too many independent or too many features. Now plotting them is a bit time consuming and also a bit difficult. So we can plot more in heat map forms, like wherever we have a significant correlation, it's going to appear in that heat map. Okay, so we'll use the heat map method from the Seabon package, and there's few things to mention, like how it should look and how it should not. But we can define the threshold. Like I'm defining the threshold like anything greater than 0.5 is a significant correlation. Now it's not a thumb rule. Sometimes we can take variables till 0.6, and sometimes we remove variables which are even greater than correlation greater than 0.4. So it is a bit subjective, but we have used 0.5. Okay. Now correlation with the target variable is always good. So the higher the correlation, the better is the variable, right? So but that's not the case with the independent features, right? The correlation, high correlation is not a good thing there. So we can have this heat map separately for target with other independent variables and within the independent features. So that way, that's the way we can select and remove some of these variables as well. So it helps in terms of feature selection as well, the basic feature selection obviously. And here you have different colors, but you see the colors are there only where you have correlation of greater than 0.5. Other cases it simply comes white, right? These cases where there is no relationship, because there's no coloring here, because the correlation is less than 0.5, and that's the threshold that we have set up. We do have is 5-6 variables here, so it's not very useful, but in case we have, let's say, 50 or 60 variables, this is extremely useful in this form. The last thing that we'll see is we can visualize categorical variable data using Boxplot. Okay, so Boxplots are very useful to locate extreme values firstly, and also making inference about the distribution of data around its mean. Okay, an ideal Boxplot that we would expect from variables is that the data is equally centered around the central tendency, mean or median. Okay, so we'll use the Boxplot from the Seabon package, and we will do. So this is where we'll do like for each type. So type is a categorical variable in our data, and in the y we'll have mileage, which is the variable of interest here, right? So we want to know how the average value of mileage with respect to each type, and if I run it, it is going to be much clearer. So here we see we have how many types? We have 6 types: SUV, sedan, Ford, sports car, wagon, truck, and hybrid. These are 6 different cars type, and we want to know the mileage with respect to these types. And we see hybrid is much ahead or much higher than the other types. The other types are more or less the same. The average mileage is more or less the same, but hybrid it is very different. And also we can see the distribution, like there is more variation of the mileage in sedan and in wagon, but there is much less variation for SUV, sport car, and truck, right? So these are some of the insights that we can get out of this box plot. We can do the same for other categorical variables also, like let's do it for origin. Here you see the mileage with respect to origin. That means whether it is the origin of the car, like where the car was manufactured, whether it's Asia, Europe, and US. You see the mileage, the difference. They're more or less the same. Slightly in Asia it is more, but otherwise they're pretty same. We can yeah we can do the same for other categorical variables as well. Okay. So that's another way of visualizing data, or doing a bit of exploration about the data that we have. The final thing that we'll do is the regression plot. Now, regression plot derives its name from the regression analysis, where we're basically trying to see how one variable is related to the other variable, and both the variables have to be numerical variable, not the categorical one. Okay, and it gives us insight about the direction of relationship, whether there is strong relationship or weak relationship, and it helps us in selecting good variables and removing bad variables. Okay, when I show you the plot, you will be able to understand how it actually helps. We'll use the Seabon package, and we'll use the rake plot from method from the Seabon in order to do a regression plot of length and mileage. So mileage is going to be our y, and length is going to be our x. Okay. So here is the regression plot. So the difference between a correlation plot and a regression plot is that we have a regression line here. So we have a least square line which passes through the middle of these data points, and that helps in many ways, right? If most of the data points are lying very close to the regression line, then it is a good variable. That means there is a strong relationship between these two variables, right? There are few observations which are lying very away from them, but they are outliers or extreme values as we had identified, and once we remove them, the relationship looks much better. But imagine a case where the regression line doesn't pass the middle of these data points, and the data points are simply distributed very ununiformly across this regression line. In such a case, the relationship is not very strong. So that's one thing we conclude. And this is some sort of a bivariate analysis which helps us in order to get down to the most important variables for an analysis, and we can do that for all kinds of independent features. Okay, we can of course write a loop which is going to give all kinds of regression plots in just one go, right? We have done that for histograms, we have done that for other sort of analysis. We have done that twice in this particular video. I leave it to you to do this using a for loop. Okay, I mean just using iteratively. Okay, so in this, so this is more or less about the exploratory data analysis, and in the second part of this video we'll see more about how to do um, uh, exploratory data analysis in Python.